All right. Good morning, everyone, and thank you for coming. I'm Francois Proulx, VP of Security Research at Boost Security. Boost Security is a Montreal-based startup building an application security product, and my team focuses on software supply chain threats. Let me start with a hot take. 2025's build pipelines look like the average 2005 PHP web app in terms of secure coding. What do I mean by that? It's a real dumpster fire. Web app security has improved tremendously over the past 2 decades, but when it comes to the build pipeline, it still lags far behind. Let me clarify what I mean by build pipeline. The modern world depends on software. We all know that. Developers write code, they mix it with open source code, everything is packaged, shipped by CI/CD. CI/CD runs with high privilege, that is, with secrets, tokens, signing keys that are in memory. It's often the bastard child, neglected by both security teams and dev teams. Up until recently, most pen testers did not even look at those targets, even though they're very juicy targets. Even if your CI/CD is hardened with strong authentication, in order to do its job, it has to accept a lot of untrusted inputs. So much so that I'd like to rename CI/CD RCE as a service. And that's because those systems run with high privilege. They're waiting to receive triggers over the network to process data and then execute code before uploading the results somewhere else. Let me fix the slide. That's more clear. In March of this year, you might have heard about a very popular GitHub action being compromised, TJ Actions change files. It's a pretty long story, but the crazy part is that based on our independent forensics that we did in parallel of other larger teams, such as Wiz and Palo Alto, we came to the same conclusion, that in fact, the final intended target was Coinbase. And since the attacker was not allowed to finish the job, as they got caught very close to the end goal, they got mad and they just put a simple memory dump snippet that logged all secrets in plain text for anyone to grab on the internet looking at workflow run logs. I equated it to nuclear fallout. Let's stop for a moment and picture where the build pipeline sits within the software supply chain. There's this amazing framework called SALSA, which stands for Supply Chain Levels for Software Artifacts. On the left-hand side, you have what they call the producer, but really I prefer to call it the developer, sitting on their laptop, writing code, using Git to commit and push to a shared repo, most often GitHub. Then they open a pull request so that other developers can code review. And in most cases, just the mere fact of opening the pull request will automatically trigger the build pipeline to run tests, linting, and other automated actions. Then this build step will, in many cases, end up pushing a final artifact to some kind of registry. In the case of open source, the registry could be NPM, PyPy, Docker Hub. But there are many more registries you could think of, including for Terraform, Terraform modules, Terraform providers, Helm charts. So now let's turn up the heat on this salsa, because there are a lot of threats that we need to consider when we look at the build pipeline, and since it's such a critical part of the supply chain as it sits between the source code and the final artifact. And also, if you remember, I renamed CI/CD RCE as a service. It's even more important to consider it when you model the supply chain. Let's walk through a typical attack sequence. We have an open source project hosted on GitHub in a public GitHub repo. It's using GitHub Actions. That's really the most popular kind of CI/CD because it comes for free. You don't need to pay for the compute. It's built in. Typically, those GitHub Actions will be used to build, package, and then distribute signed artifacts. in the case of the attack, you need a workflow that triggers on a so-called risky event. That could be pull request target, workflow run, issues, issue comment, and there are some more. And the real reason why it would be considered risky is that those expose secrets in the memory at runtime, even when executing against untrusted code from a fork. So then that workflow needs some kind of vulnerability. More on that in a moment. Ultimately, the attacker's goal is going to be to dump the memory of the runner so that they can exfiltrate all secrets that are in memory during the execution. And the reason is that most of those runners are effectively just VMs that were spun up on demand for the given job. And they typically grant sudo access to the code that runs. And most of the time, those exploits can be zero-click and leave few traces. This might look like a subway map to you, but it's actually the full attack tree for GitHub Actions. There are many possible mitigations and many ways to route around some of them. What kind of vulnerabilities are we talking about here? First, we have the so-called pull request, which is really when there are files contained in a pull request that would modify the behavior of existing tools present in that build pipeline. That's why we came up with the term living off the pipeline. More on that in a moment. Second, we have template injection, those mustache expressions with the curly braces. But really, we should just say it's command injection or script injection, depending on the context where the expression is interpolated. Third, we have bot-mediated confused deputy. That's a very fancy way of saying that if the pipeline already trusts certain non-human identities, for instance, dependabot, to run certain high-privileged action, for instance, automatically merging the dependency updates to the main branch, sometimes, and really depending on the authorization logic as part of that pipeline, there may be ways to game the system and effectively bypass those authorization checks. Finally, we have self-hosted runners that are not ephemeral. If you recall, earlier I renamed CI/CD RCE as a service. And keep that in mind when you consider that a runner is just a VM, as I said, which typically is going to be a hosted runner, which the VM is just spun up for that exact moment and then trashed. But if you decide to self-host, for some reason, you might need a more powerful CPU, some GPUs, or other access to other resources, then you're responsible for hardening and ensuring that the RCE is not going to allow to pivot laterally to other systems, or just extract the secrets from other jobs. What does a vulnerable workflow actually look like? Well, let's look at it together. This one is running on a risky trigger, as I said, pull request target. That's only one of them. Also, it's not explicitly setting the permissions of the GitHub token. So it may end up, depending on the configuration, to have the default read-write permissions. Also, because that pull request target is not specifying a filter on the branches, there may be options to revive from the dead this kind of vulnerability, and I'll give a concrete example in a moment. Then we have a container in that case, so some jobs might be configured to run based on a Docker container, and that container might have other vulnerabilities that we cannot see by just looking at the pipeline file. Then the workflow is checking out the untrusted code from the fork. It's also using another secret, not the default secret, that appears based on the name, to have read-write access to other repos than the one that's being targeted. Finally, we have make, which is going to be using the make file that, in this case, the attacker has full control of. Then they have RCE. On the right-hand side, you have a bonus Git branch name injection. So when you open the PR, you have your fork, you give it the name of the branch that you want, and that will be injected as the mustache expression at the bottom. So then that's another way to get remote code execution. So does this only happen on GitHub? Absolutely not. All modern CI platforms that trigger on events from source control systems, such as GitHub, may be vulnerable. So that's also the case on GitLab, ADO, Circle CI, OpenShift, Pipeline as Code, Travis CI, Jenkins. Basically, all modern CI that will trigger on those events, when the PR opens, for instance, and depending on the configuration, they may expose secrets even on more risky contexts, such as untrusted code from a fork. Basically, the devil is in the details. So last year at NorthSec, we told you all about our package supply project. In the months that followed, we rewrote it from scratch in Go. The reason is that we could benefit from our own open source scanner called Poutine as a core building block. And that makes it more scalable and extensible so that we can optimize the detection rules with custom rules and rescan in just about an hour the entire data set. Also, we shifted our focus from simply gathering as many GitHub repos as we could find to first manually curating a list of known entities. Entities being corporations, governments, universities, nonprofit organizations, large open source foundations such as Linux Foundation, so that we would first have an entity and then find associated GitHub organizations. In the case of Google, for instance, we found over 100 GitHub organizations owned, managed by Google. In the case of Red Hat, 120. US government, federal and state entities, 340. For each of those organizations, we can often see hundreds, if not thousands, of public GitHub repos. So you can start to see the number of pipelines we can find across all of those repos. The advantage is that now we have a central entity that is potentially the right point of contact to perform responsible disclosure. I mentioned Poutine. So what is Poutine anyway? Poutine is our open source scanner that is specialized in finding vulnerabilities in build pipelines. It's very efficient. You give it a read-only token to GitLab or GitHub. It will automatically discover repos, index them, and scan to find vulnerabilities. Under the hood, it's using Rego. Rego is a language that is very easy to extend, and in this case, we create a domain-specific language that allows you to write your own rules to detect certain patterns. So it's very easy for you to clone the existing rules, adapt them to your own needs. One cool and very unique feature we added pretty recently is the ability to scan just as efficiently on remote stale branches. The idea is that when it comes to workflows that trigger on pull request target, because you can effectively open the pull request against any remote stale branch that may contain an old version of the workflow, you can basically revive from the dead vulnerabilities that have been fixed in the main branch but have been forgotten. You may wonder how prevalent this vulnerability class really is. Well, based on a recent snapshot of package supply, we had over 200,000 findings. Most of those are low confidence, basically what comes out of the open source version of Poutine. Then we have our own internal rules, which are more precise, and that's what we would call like high confidence. So we have about 10,000 findings out of that. And the idea is that we focus not just on vulnerable workflows, but we try to validate as many exploitability criteria as we can, as well as ensuring that there's an interesting secret to exfiltrate. So, for instance, if the secret would just have a read-only access, we would ignore such a vulnerability. After that, we triage those 10,000 and find about 24% are easily exploitable, and we need to report them. Then there's some more, about 42%, that are just as easily exploitable, but there's an environmental condition that prevents it from being exploited at this moment. For instance, if the workflow is present, vulnerable, but has been disabled. So if someone were to re-enable it, or we've also seen cases where there's a dependency that makes the workflow crash. So if something gets updated, it might suddenly make it exploitable. Now, let me tell you a story. Picture this. It's mid-August 2024. We spin up the first working version of package supply v3. Just a week later, it catches a regression in a very popular Python library. In fact, a GitHub action associated with it. It's called Ultralytics. So in the Ultralytics GitHub action, I had seen a very similar vulnerability a couple of months before. It had been reported, fixed. In that case, it was basically a regression, a very similar vulnerability. And I kind of ignored it because there was something much more interesting that we had just found. Around the same time, we found vulnerability in several workflows on 22 repos owned by Google. We reported those vulnerabilities to the Google Bug Bounty, their VRP program. A couple of weeks later, they report that it's been fixed. We check, indeed, it's been fixed. We're waiting to know how much they will pay out. And in the meantime, our system catches a regression in Google's workflows. We report it yet again, they accept, fix, and then they paid twice the bounty. Fast forward to December 2024, news breaks that Ultralytics, if you remember, was compromised using by adding a Monero crypto miner. And it was done using the exact vulnerability that we had discovered and forgotten in August. So we got very frustrated about this, that we had missed it and kind of forgot, being swamped with other things. Every quarter we have hackathons, and this time we used it to kickstart a new project called Package Threat Hunter. The big idea is that now we not only scan for vulnerable workflows, but we ingest the entire fire hose of GitHub's public events in near real time. So it's about delayed by 5 minutes if you, that's a constraint based that GitHub gives. We process the events, we cross it with various data sets, and then we can hopefully catch build pipelines exploits as they happen. Barely 10 days after the hackathon concluded, it's Christmas holidays. Another hack happens on Kong Kubernetes Ingress Controller. Because it's the holidays, basically no one notices, even the maintainers of Kong, until we come back in January. We all see the news, then we look at our own data that we had in Threat Hunter, and we could see that we had all the data to make a forensics timeline, also even more detailed than many other folks could do because we have extra data. A couple of weeks later, I get the idea to use a dark web threat intel tool by this startup in Montreal called Flare. I think they're right here. So pretty quickly, I find a couple of very interesting forum posts on a cybercrime forum called Breach Forums. In early December, a new user creates an account on Breach Forums. They start by talking about how to remain anonymous online. And here's the real nugget. 12 hours before the Ultralytics hack, they drop the exact 0-day, copy-paste the snippet with the line of code that's the actual vulnerability, with links to Poutine and the living of the pipeline resource on our website. Then, based on the forensic timeline, we know at the exact moment when the attack happened. 24 hours after the hack, the same breach forum user comes back and is starting to brag about it by saying someone used PRs to leak secrets from pipelines. They used it to drop a Monero miner, which yielded very little, but it caused chaos around the world. And then the user is never used again and never posts again up until this day. I'm not here to give this person any more attention than they deserve, but I would say that the timeline of events is rather strange to me. End of the story. Let's shift gears back to Package Threat Hunter. On the left-hand side, you have the architecture for Package Supply v3, which is all about finding vulnerable pipelines, triaging them so that we can responsibly disclose. On the right-hand side, you have Package Threat Hunter, which is all about ingesting the GitHub firehose of public events. It's also designed to ingest our customers' enterprise audit logs. Then everything gets fed to a microservices architecture, which enriches with other data sets, such as the vulnerabilities from package supply. There we have a bunch of detection rules, and the events and detections go to a data lake, in this case, BigQuery. That's where we also build organically personas of the different users we see interacting with different projects on GitHub. More importantly, we tag those different personas with various criteria, and of course, the goal being to tag if they appear to be exploiting pipelines. Of course, that requires putting a lot of pieces together to make that call before we can send it for internal review. Now, this funnel chart really puts things into perspective in terms of signal-to-noise ratio. We start with about 5.5 million public events daily. The vast majority of them are push and pull request events. Then we trim along the way as we determine if it's a critical open source project or someone's personal pet project that doesn't even have a build pipeline, for instance. We still have about 500,000 events to deal with at that moment. Then we enrich with other data sets and various signals so that we can flag about 46 events on average daily. Once we have the events and we triage them as being noteworthy, we can import them to a visual timeline tool so that we can build a forensics timeline. As we discovered more and more vulnerable pipelines, we needed to start to attribute a risk rating. First, of course, we thought about CVSS. Very timely here. And in fact, we started by basically forking the CVSS 3.1 calculator. We adapted the base metrics to be more relevant for pipeline. And we built, instead of CVSS, we built the PVSS, so which is the Pipeline Vulnerability Scoring System. So the reason is that, yeah, like build pipelines have certain criteria that don't apply very well to normal CVSS. But as we added more real-world data into the calculator, we realized that the formula behind CVSS 4.0 would be even better. So it's not quite ready for prime time, but hopefully we plan on open sourcing the calculator in the next couple of weeks. Now let's jump to the blue team section. Most of you are familiar with MITRE's attack framework, but there's also this supply chain alternative variant of attack that's called OSCAR, which stands for Open Software Supply Chain Attack Reference. We did not come up with this resource, but what we did is that we took it and created a profile to focus just on the TTPs that are relevant for exploiting build pipelines. Already, we narrowed it down quite significantly from the original OSCAR matrix, but we can further simplify it and focus our attention on the TTPs that are most common. So really, the common scenario of a vulnerable pipeline that can be exploited using LOTP with the end goal to backdoor the final artifact. Throughout this talk, I mentioned multiple times living off the pipeline, or LOTP for short. Let me add a couple of more details about that. A LOTP tool is one that is already present and being executed by the existing legitimate pipeline. And since the attacker is not allowed to modify the pipeline and trigger their own version, and that's a core defense mechanism by design of GitHub Actions, for instance, of course, that would be too easy if you were able to just modify the pipeline. You have to live with the existing tools, the existing pipeline. So, you have to live with it. So the gotcha is that in most cases, command line tools expect to find a configuration file in the current working directory. You can find our LOTP catalog at this address. We've already documented about 45 tools already, and it contains all POC payloads to really make it easy for you to understand how it can be used. We have about 25 more tools just waiting to be fully documented as GitHub issues. So if you want to help out, you can go and pick a GitHub issue and add the extra documentation. Let's look at two very representative examples. First, we have mkdocs, which expects to find a configuration file, namely mkdocs YAML. In that YAML, you can specify hooks that point to arbitrary Python code. Also, here we have Trivy. Trivy is a security scanner that scans containers, for instance. But you can, in the configuration file, you can specify the template so that the output is custom. And that template is using Go template syntax. That gives you a limited form of RCE, but still enough to exfiltrate secrets, which could contain sensitive tokens, and exfiltrate them via DNS-based techniques. Another variant is tools that don't expect a configuration file, simply don't have a configuration file. But they might behave differently if an environment variable is present. Obviously, because the attacker cannot simply modify environment variables externally, that may still be used as a second-order RCE. In fact, we've seen real-world examples where poisoning bash before another job is started might be useful. So you might effectively change the behavior of bash that is about to run, and that can be kind of second order. Time to wrap up. Can we actually use these techniques to predict the next attack? Maybe. It's not going to be easy. Attackers appear to have only just started to use some of those techniques, so we might be ahead of the curve on this time. Or maybe we missed a whole lot. Either way, it's clear that when you think that CI/CD is more like RCE as a service, you can understand why it became red teamers' favorite soft spot. If you want to learn more, check out our blog. We have different projects hosted on GitHub. We have a couple of positions open in the research team, as well as internships. And there's a few quick shout-outs to other fellow great researchers that made amazing talks at DEF CON last year. Thank you.